So, good evening, friends who are from India and Asian continent, and good morning or good afternoon to friends in Europe and other places. So, Pramey, I think, is in India. So, good evening to you. So, many thanks, Pramey, for kindly accepting our invitation to join this W2A seminar. Today is the 89th webinar. We began that activity somewhere in 2020 in June, so it's going to be 2 years soon. Yeah, so thank you very much on behalf of my team, Braj, Puspendra, Sakti, Soyang, Ajar, and all. We like to thank you, and also we like to thank all the participants for kindly joining. I think Pramey is an emerging star in Spintronics, and probably already known to many, but I would just give a very brief formal introduction about him. Pramey is currently working as an assistant professor in the electrical and computer engineering department at the Purdue University in US. Before joining Purdue, Pramey was a postdoctoral scholar in the physics and astronomy department of UC Los Angeles with Professor Yaroslav Sesunak, very famous theoretician. He earned his bachelor's degree in electrical engineering from IIT Kharagpur in 2009, and then master's and PhD degree in electrical engineering from UC Los Angeles in 2011 and 2015, respectively, under the guidance of Professor Kang Wang. His research has been at the interface of theory and experiments, focusing on classical and quantum spintronics phenomenon and their device applications. Along with his teammates, this work has resulted in one of the earliest demonstrations of current-induced room temperature fermion manipulations, spin torque switching by topological surface states, quantum sensing of spintronics phenomena, and nanosecond fluctuating probabilistic beats. He is the recipient of NSF Carrier 2020 and Purdue Outstanding Engineering Teacher Award and Qualcomm Innovation Fellowship 2013. I'm also very happy to say that Pramey and me, Professor Bhaskaran and Professor Antonio Azevedo from Brazil, we are actually co-editing a special issue in IOP journal, Materials for Quantum Technology, and the issue is open for submission of articles. That maybe I can show in another talk as a slide. But happy to work with you, Pramey, and looking forward to your talk. I just like to make a small announcement that during the lecture, we don't take any questions. So if you have questions, then kindly write in the chat box or raise hand. And at the end of the lecture, first we'll quickly take a group photo, and then we'll have the question answer session. So with this brief note, Pramey, I think all yours. So looking forward to your lecture. Thank you so much.
All right. Thank you very much for the kind introduction, and very happy to be part of the W2S seminar series. There have been many great talks already. I have listened to many of them, and I'm very happy to contribute to one of the such talks. So today, what I would like to tell you about, by the way, before I start, is my laser pointer visible to everyone?
Yes, yes.
Okay, cool. So today I would like to talk about this sort of new emerging field of hybrid quantum spintronics, which really tries to combine classical and quantum spintronics world together. And in what sense is what I would like to give as the main message for today's talk. So in order to do that, before I do that, I should thank the people who actually really contributed to this work. My postdocs, Avinash, who has really done all the theory for most of the work that I will mention. He's now moving on to Intel. And experimentally, Abhishek is the graduate student who has done most of the experiments that I'll be discussing. Another graduate student who has helped in the theory is Mushfikar, and lastly, the undergraduate intern from IIT Bombay, who's now at MIT, Shivam, contributed to some of these works. And of course, a lot of this would not have been possible without the help of collaborators. It's a long list to thank them, but here are the main contributors that have worked, whose work I will be sort of also advertising here, and of course all the funding sources. So in order to talk about the field, just introduce the field, let me present the following view of spintronics, where all of our audience are aware that the basic essential quantity that we would like to harness for all spintronics applications is the spin degree of freedom. And what we learn in quantum mechanics is that the spin is at the very core of it is a quantum mechanical object That is to say, if the system has some spin S and we were to measure the spin, I'll only see some discrete components of the spin along certain measurement directions. So it is inherently a quantum mechanical object that we are trying to manipulate. But there have been two various regimes in which the research of spintronics have focused on harnessing this degree of freedom towards an application to memory, computing, communication, and sensing applications. And along this path, they have discovered various kind of phenomena of fundamental interest as well. And largely speaking, these two paths, the paths that people have taken from bottom here to harness the spin towards these applications, can be drawn in two independent directions. In one case, the research community has focused on the so-called macroscopic or classical limit, where the spin is a large number, large as compared to the thermal scales or time scales involved. And as a result, in such situations, we can disregard any discreteness in the spin, and you can think of the spin as just a classical vector. This famous example is like a bar needle of a compass needle or a bar magnet. And that's the macroscopic limit that people have focused on. On other extreme, people have also focused on the case where the spin is really like a few microscopic limit, few spins, like single spin electrons. And there, this discrete nature is really at the heart of it. And the way these kind of two different limits have contributed towards this goal of creating new kind of memory, computing, and communication sensing technologies, there have been several excellent talks already in the WTS seminar that we have listened to. On the macroscopic side of things, the nice promise these magnets have is that now people can actually engineer the interactions, spin-spin interactions quite well and create building blocks ranging from single spin, like such that the whole of this magnet, that is the vector that we were talking about, behaves like one giant spin, or you can engineer configurations which are topologically non-trivial, such that that comes with this added advantage of topological robustness. Or you could create building blocks. You can utilize building blocks which are like wave-like excitations of these vectors that I was talking about. So we're utilizing these basic building blocks and with the added ability to control the spin via various degrees of external norms. For example, one can control it mechanically, thermally, optically, by applying currents, or by applying voltages. You have heard several talks in WTS for each of these type of controls. Those type of controls, in addition with the fact that you can create sort of desired energy excitations inside these material systems, you can utilize this physics to create compact realizations of applications that one wants to create. For example, taking an example from one of the recent WTS seminar, you can create a magnet which can fluctuate between up and down state. And these fluctuations can be utilized, if you can tune it by voltage, you can utilize this to create a probabilistic bit. That particular compact realization, if you want to create via utilizing transistors, it will take roughly about on the scale of hundreds of thousands of transistors to create that functionality. So the fact that you can utilize this nice physics to create compact realizations typically gives rise to energy efficient, tunable systems, which promises better next generation memory, computing, communication, sensing technology. So that's the advantage that these magnets bring in on the classical end. Likewise, on the quantum end, or in this microscopic limit, people have focused on the single spins, which are basically paradigmatic example. Two-level quantum system is a paradigmatic example of a qubit. And this quantum bit, you can control it. People have various ways of creating these qubits. For example, inside defects of a lattice, they can create such sort of spin defects, and they can control it by applying external microwave drives to drive this particular qubit. At the same time, you can use light, for example, to read out this qubit, and you can start creating systems which starts to entangle two of these qubits and create a larger and larger processor. So as a result of this, these spin systems have, if you focus on this quantum side of things, you can utilize quantum coherence to create, again, new classes of memory, computing, communication, and sensing technologies. And there has been a lot of research in that direction as well. The quantum coherence, again, is the main thing, is the fact that you're doing something which the classical systems don't allow you to do. You're utilizing these nice quantum coherences to create, utilize physics which was not possible in the classical domain. So that's the main promise on this quantum side of things. So these two paths have been usually taken separately, and there's not been much intermixing between the two. What this talk is focusing on is trying to intermix the promises that people have shown in the two fields to solve the challenges within those two fields. And that is giving rise to sort of a new hybrid interface quantum spintronics field, which is what is the main focus. And that's the main message I want to convey to you, that by taking advantage of the promises within both fields, one can solve challenges that the two fields are facing. All right. So, and I will demonstrate this particular thing by picking in a specific example. I'll pick up from the classical end these magnon or spin wave-like excitations and combine it with this defect-like spin qubits and create a hybrid system which combines these magnons with spin defects and show why that system could be an interesting system to look into. Okay, this is a pictorial representation of this microscopic world and macroscopic world coming together to create a hybrid which can have various interesting applications and phenomena to be discovered in. Right, so that is the main message I would want to drive towards during this talk. So the way we'll approach this is, the main outline will be, I will first talk about the two systems individually. That is, I will introduce this microscopic system, which for us would be optically active spin defects, and discuss why this is a promising system and what are the challenges in the field. And at the same time, then I'll switch gears and talk about the macroscopic system, which is basically wave-like excitations of these magnets, which we will be calling magnons now. And we'll discuss about the promise and challenges there. And then we'll combine the two systems and talk about why do we even want to create these hybrids, and give several examples of why making these hybrids would be is a promising direction. Okay, so with that, let me begin with discussing the first microscopic part of the system. So the microscopic part that we'll be focusing on as an example is the nitrogen vacancy in diamond. So this diamond over here is essentially a carbon lattice where you create a defect inside this carbon lattice. The defect is of the following nature: you remove one carbon, put a nitrogen in, and you remove another carbon nearby, such that this is a vacancy. So this defect over here is called NV defect. And the NV defects we will be focusing on will be additionally charged with an extra negative sign. So as a result of this, what happens is this defect at this traps, effectively you can think of it as two spin half electrons together at this site. And this two spin half, when you put together, again, something that we learn in quantum mechanics, we create a spin 1 system and spin 0. That's the additional of angular momentum rule. So that is the effective system we are dealing with in these defect centers. And they are well trapped inside this nitrogen vacancy center. And this host lattice, which is carbon, is a very good insulator. So all the electrons that are there inside this insulator, they are much far in the gap, and these defect states that we'll be talking about will be lying within the gap of the host lattice. So as a result, these electrons don't interact that much with the lattice, and as a result of that, it's a very well protected defect center. Now, to think about how should we think about this defect center, as I mentioned, it is effectively like two spin half systems. It turns out that the spin 1, if I combine two spin half systems, the effective spin triplet that comes out as spin 1 system will be the ground state of it. So that's the energy diagram that I'm showing of the defect. So these three levels over here are talking about the three levels of spin 1. So in our original picture, these are essentially the spin projections along these NV axis can be -1, +1, or 0. Those are these three states that are shown in the triplet, and they happen to be the ground state in this case. And that ground state can be described by the following Hamiltonian. That is to say, since this spin 1 is not in vacuum, it is in some lattice, there is a preferred axis along which this spin 1 tries to point along. That is to say that this spin 1 wants to, if the projection along this NV quantization axis is 0, that happens to be the lowest possible energy state. And if the projection is +1 and -1, that lies at a higher energy as compared to this 0 state. And that is described by this first term over here, where this is called the so-called zero field splitting. If you put SZ +-1, this is a higher energy. And if you put SZ0, this is lower energy state. And that's exactly what you see in this level diagram over here. Additionally, if you apply external magnetic field to this center, that can interact with the spin with the usual Zeeman coupling. So that is that part of the Hamiltonian. So this ground state over here can be described by this very simple looking Hamiltonian. Now, the spin 0 part of it turns out to be lying at a higher energy. That's the singlet states. They tend to lie at higher energy over here. Right. So that is the spin structure of the system. On the other hand, if I focus on the orbital degrees of freedom, these electrons also have wave functions, orbital degrees of freedom, and there is some excited orbital states that lie at higher energy. And these excited states can be, you can excite them via application of light. So for example, this center, if you shine green light on it, it will absorb this green light and it will come down and radiate back red light. So you can actually view this system, read this system out optically. The nice thing about this sort of optical process is, as shown in this diagram over here, is as if the spin was in +-1 state, the system can go up and come down along two different paths that are shown here. That is to say, it can come down directly, or it can come down via the singlet states to the state 0. So it turns out that this singlet path is a dark path. It does not radiate. Only this path radiates. So this has very important consequences. For example, if your state of the system was in the state +-1, and if you keep on shining green light, after certain cycles, this population will be transferred into the state 0. So as a result, you can use just light to initialize the system, this quantum system, into a state 0. At the same time, if the state is in 0, it goes up and only comes back. So it preferably populates state 0 if you keep on shining red light. So that allows us to optically initialize the state into state 0. At the same time, the same phenomena allows you to read out the spin state of this center. Because if it is in +-1 state, it gives off less light as opposed to the if it was in the state 0, because of the fact that if it was in +-1 state, there's a dark path that is available for it. But if it is in 0 state, there's no such dark path. It fluoresces more. So as a result, if you just monitor the amount of green light that is, the red light coming out of this defect, you can tell whether the system is in state +-1 or is in state 0. So this allows to very nicely read out the state of this defect center. Now, on top of this, you can manipulate it, the spin state of the system, if you focus on this low-lying manifold. If you come in and shine in some microwave field, let's say apply a transverse microwave field at an AC frequency which matches, for example, 0 and +1 splitting over here, then you can drive oscillations between these two states, the so-called Rabi oscillations. And as a result, you can control this qubit that is now defined by an external DC field. So you separate out +-1 state by applying a DC field, and then you can drive microwave and control the state of the qubit between 0 + 1. If you choose the microwave to lie between 0 and -1, you can drive the state from 0 to -1. So as a result of all of this, you can use microwaves in combination with light to manipulate and read out this quantum object, which is a very well protected object, which can show quantum coherence up to room temperatures. That makes it a very, very exciting defect center and has given rise to many applications, as I mentioned now as the next step. So the promise of these defect centers is people have come up with ways to use these as quantum memories. So you can shine light and store these quantum information of light in the spin state, and spin state survives for a longer time. In fact, there is a nuclear spin which is sitting next to this nitrogen. You can transfer spin from the electron spin to nuclear spin, and nuclear spins can maintain coherence up to very long time, on the order of seconds, also to hours. And as a result, you can store quantum information inside these defect centers for very long time. So they act as very good memory elements. As I mentioned, you can entangle two such centers together and start performing 2-qubit gates. This was the work which demonstrated a programmable 2-qubit based on these nitrogen vacancy centers. So such proof of principle demonstrations have been done. And the main promise of these defects is that all of this can be done at ambient conditions, which is very much a rare fact in the quantum world, right? So that's the main promise in the memory and computing. On the sensing side, it has emerged as one of the very nice nanoscale sensor of magnetic fields, because now these spins interacts with the magnetic field. It changes the spin state, which you can read out optically. So it acts like a very good magnetometer. The nice thing is it's atomic defect. So depending on how close you can bring this to a particular sample which you want to sense, for example, in this example shown here, one was sensing this spin via this defect center over here. You can really get a nanoscale resolution based on how close you can bring this defect center to the sample. So you can, on a nanoscale, map the magnetic field emanating from some sample. Okay? And this magnetic field there are various sensing protocols that has been established for sensing these magnetic fields, which allows to sense fields from right from the DC values of fields up to the gigahertz frequency resolution. So you can have very high nanosecond time resolution as well as nanoscale spatial resolution. This defect center, as I mentioned, maintains its quantum coherence even up to room temperature. So it acts like a sensor from, you can sense various kind of applications from cryogenic to room temperature. And it is a very non-invasive way of sensing the magnetic field because this tiny defect center does not perturb a sample that you're trying to sense. So as a result of that, combining these four facts, which is very rare again to find in a sensor, this emerging NV center has emerged as a very nice sensor for probing various kind of condensed matter physics phenomena because of the magnetic signals coming out of various magnetic films or superconducting films. At the same time, it has found applications in biology. So the main thing I want to get across here is these defect centers, these spin defects, quantum spin defects, have a very important memory computing and sensing type of applications because of these nice properties that people have demonstrated. Now, the field is not without challenges. As you can see that for the computing side, memory computing side, I was showing only very few NV centers. There were just 2 defect centers type of systems that have been shown, demonstrated experimentally. There's a main challenge there is how do you scale the system beyond 2 NV centers? On a chip, how can you create a large ensemble of these centers which you can individually control and address? The problem is the entanglement that is done to create 2-qubit systems for these NV center spins is they utilize dipole-dipole interactions between 2 spins, which falls off very quickly. And as a result, as shown over here in this figure, as soon as you go beyond few tenths of nanometers separation, the 2 spin systems are no longer entangled. Okay, so as a result, you have to place them very, very close to each other. But optically, if you want to read such centers, you need to use laser which spot sizes of the size of micron. So hence, you want to at least separate them by micron sizes if you want to read them individually. At the same time, if you want to manipulate these centers, the current way of manipulating, as we discussed last slide, is via microwave. But this microwave, as we know from Spintronics, is very hard to localize on the scale of nanometer sizes. So then what one really needs is some local control, like a voltage control of these NV center spins. And at the same time, we need something which can mediate entanglement between these centers, even if they are separated by micron sizes. If such systems can be developed, then one can start thinking of scaling the system beyond the prototype of 2-qubit systems that are shown. So that's one challenge in terms of the number of spins you can use to perform a particular application. There is another scaling challenge where on the sensing side, right now, these are very good sensors of magnetic fields because spin interacts very well with the magnetic field. But if you want to sense something beyond magnetic field, can we scale the sensing capabilities beyond magnetic field? For example, using electric field. So people have demonstrated, in fact, electric field also can interact with NV centers. And they can, by indirect coupling with spin, the so-called Stark shifts, you can still sense the electric fields coming out of different samples. But the problem is the sensitivity is very tiny. So now the main thing is, can we find ways to sense things which are beyond magnetic field, like electric fields, and can we improve the sensitivity of these sensors for such phenomena? Because then you can translate all these advantages of nanoscale probing, room temperature to cryogenic to electric field systems, and that will open up more type of systems that one can sense. So those are the main challenges the field is facing for this microscopic world. Now I'll shift gears, and having discussed and introduced the promises and challenges of these microscopic world, I'll talk about the macroscopic world, mostly focusing on magnons. So magnons, as most of you would know, that it's the collective spin wave-like excitations of these classical magnets that we are talking about. So a magnon is essentially a single quanta of this, but mostly we are focusing on the spin wave excitations of these classically ordered system. And these excitations themselves are very promising for constructing something called Magnonics in the field of Magnonics, where one tries to utilize these collective excitations for processing information. The advantage these systems have is they are free from Joule heating type of effects because the propagation of these waves don't require electrons to move across the system, and as a result is free from ohmic heating. On the other hand, they have these naturally they have very nice type of properties. For example, you can these magnetism naturally breaks reciprocity. That is to say, a wave moving like from left to right and right to left could be very different. And if such capability is available, you can create various kind of nice circulators or applications where you would want to transfer information from A to B, but not from B to A. So for such applications, also these objects could be very interesting systems. On the other hand, as you mentioned, all of these magnons, because the spin can be controlled by various degrees of freedom, you can control this via various external knobs, and hence start thinking about creating computing, memory, and similar applications utilizing magnons as a basic building block, which has given rise to the field of Magnon spintronics. Now, on another hand, these magnons, as I just mentioned, because it can couple to various degrees of freedom, it can act as a universal transducers, resonantly enhanced transducers. So if you're familiar with plasmonics, the whole idea is that plasmons can resonantly enhance near electric fields near to the sample. Very similarly, magnons can enhance microwave fields in the gigahertz regime in the near field. And as a result, you can use these to actually couple to various different degrees of freedom. Just like here, you can control mechanical degrees of freedom, couple heat, optics, and electronic degrees of freedom. So it can act like a very nice transducers which are resonantly enhanced. And at the same time, the spectrum of these magnons carry information about the ground states, various kind of exotic ground states the magnetic systems can have. And that can provide a window of looking into what are the ground states. Can you image the existing ground state? An example of that I'm trying to show over here in this central figure, where what I'm showing is an antiferromagnetic domain wall. So think of this blue region as two spins pointing like this, up and down, and the yellow region as the opposite of these configuration, that is A pointing down and B pointing up. And there's a domain wall lying in between. Now, it turns out these antiferromagnets are very interesting candidates for very fast, creating very fast processing units. And hence, one wants to know ways to probe such antiferromagnets. The fact that this is a sublattice which has both up and down spin, the traditional probes of magnetism face challenges because this does not give rise to very strong magnetic fields coming out of these antiferromagnets, which, by the way, is a promising fact of antiferromagnets because you can put many antiferromagnets together without one affecting the another one. But that is also challenging because now you cannot probe such systems. But it turns out that if you look at the excitations above this system, that is the Magnon wave-like excitations above this system, their spectrum is very special. Their spectrum inside the domain region has a very large gap. That is what is shown here, this delta, because it's a very high frequency excitation that has on the order of terahertz type of gap. On the other hand, the domain walls, they are very soft object. You can move them around without paying much energy. And as a result, they host gapless modes, very low lying frequency modes. So if somehow you can probe these magnons, which are there in the domain wall, you can image the domains inside antiferromagnets via just conveying that information is conveyed, is carried in the excitations, the Magnon-like excitations of the system. So that's just one example of where the exotic ground states you can probe via using excitations of the system. At the same time, this was a proposal coming from Amir's group at Harvard, where you can now start thinking of magnons as just like probe particles. Things like neutron scattering experiments you can perform with magnons. So you can, for example, excite these spin waves and then throw it on some target material which you want to probe, which interacts with these magnons via various interactions. And you want to probe the scattering cross sections of those interactions. So again, if you had an ability to image these magnons somehow, then you can, by imaging those magnons, you can extract information about the scattering potential of these different, and you can understand various kind of interactions like Zaloshinsky-Moria and various interesting interactions which people look in the classical spintronics physics. Right? So that's the promise of magnons. They can act like very nice probe particles for conveying a lot of information about the underlying physics. And at the same time, they act like transducers of various kind of external fields. They can resonantly enhance these external fields. And if, again, we can somehow image these magnons or probe these magnons, we can probe these external fields very nicely because of this resonant enhancement. And at the same time, they can allow to as an information carriers. So that's the promise the field has for Magnonics. Now, the challenge, of course, here is how do you actually go ahead and locally probe these magnons? Right, so these on a nanoscale, nanosecond time scale. because if you can do that, then all these various applications can be enabled. So if you want to, for example, create a system of antiferromagnets or nanomagnetic antiferromagnetic systems so that there are no domain walls, you would need a way to image such systems. So to advance these fields, there should be a ways to probe these magnons, particularly in insulating systems where these systems are free from Joule heating. So on the other hand, you cannot pass currents in the insulating systems. It's all traditional probes of electronics. And at the same time, if you want to image, let's say, a nanoscales object, so you cannot use light probes like there are various kind of magneto-optic probes which is used for imaging magnetism. But all such systems become challenging on these nanoscale, mesoscopic type of systems. So then one needs new ways to probe such magnons. Okay, so with that, the main messages I hope that I've sent across is both these magnons are very interesting objects for classical side of things, and these microscopic qubits are very interesting objects on the quantum side of things. They hold various promises, but both of these fields have challenges. And what I want to show is if one creates these hybrids, the promises that I just mentioned within the two fields can be leveraged to solve the challenges that I also highlighted right now. So that is the main goal of my remaining talk. And that is the reason why one would like to create these hybrid systems of microscopic and macroscopic qubits. Okay. So for example, on one end, one can utilize these macroscopic spin wave-like excitations to act like on-chip coherent fields, because these these magnon excitations, they emanate whenever there is a magnon excitation, they give rise to microwave fields coming out of them. And these microwave fields can interact very nicely with the spin qubits because of strong interaction between spin and magnetic field, and hence can act like on-chip control fields or mediators between two spin qubits. Remember the challenge that we discussed, that if you want to connect two spin qubits which are far off, magnons could be a very nice object that can do this, because magnons can travel to long distances, something that is utilized in the classical spintronics. At the same time, it resonantly enhances microwaves, and as a result of that, it can very strongly interact with spin qubits. Okay, so then these sort of things, that's one motivation why people want to create such hybrids. On other hand, if I now look at this, view this spin defect as a magnetometer, as we mentioned, it is a nanoscale magnetometer, can map out local magnetic fields coming out of these various macroscopic systems. This magnetometer can be utilized to probe these magnons, the challenge of probing magnons on a nanoscale, nanosecond time scale. Okay? And what I want to do show you is some pictures of where people have actually utilized this, these things that I just mentioning right now. So for example, in this experiment done by Oshlom's group, it was a beautiful experiment where they demonstrated the following fact, that each of these nano diamonds that you show over here, these are basically these defect centers that are sprinkled on top of an yttrium iron garnet. That's the magnetic film, which will host the magnons. And what was the experiment that was shown was, if you drive these magnons with a microwave field, they can travel to a long distance away from the strip and then locally drive this nano diamond over here, perform Rabi oscillations on these nano diamonds. You can manipulate this qubit via magnons. If you remove this YIG film, the microwave strip line is too far off from these nano diamonds, and there was no such driving that was observed for these nano diamonds. So it was observed that by putting a magnon film, you can enhance the interaction between microwave and the nano diamond. This is exactly the effect that I was talking about, that magnons act like local enhancers of these microwave fields. There's another recent demonstration where one utilizes the fact that these magnons now can be excited electrically because of the fact of spin orbit torques that one can apply on these magnetic films. And as a result of that, these locally, you can just apply current and use current to drive these NV centers. So what was demonstrated here was that the Rabi oscillations was enhanced if a current was passed through this combined film system. Okay. On the theory end, people have shown now, if you put two of these defect centers, even micrometers apart, these magnons can be utilized to entangle these two qubits. And this could solve the challenge that I mentioned of having two defect centers far off and still being entangled. And there have been few theory papers that have recently demonstrated that this is possible. Again, waiting an experimental confirmation. On the end of using these as probes, Now, on the opposite end of using these defect centers as probes of various kind of phenomena in these magnetic films, what people have shown is, again, in this work, these defect centers were utilized to probe the local chemical potential of magnons. So magnons was excited via strip line into some non-equilibrium population, which can be characterized by some effective chemical potential. And these NV center spins via the magnetic field signatures that was coming out of such films was used to probe this chemical locally on a nanoscale, probe the chemical potential of these magnons. One can image in this experiment over here, one can even image. So here it was more like an incoherent population of magnons. Here it was used to even image the coherent driving of these magnons, the phase information that these magnons carry. One can image the phases using these NV centers as probes of the magnetic field that is coming out. On other hand, in this work, we propose, as I just mentioned, that the domain walls can host, within antiferromagnetic domain walls can host very low frequency excitations. And as a result, if you scan an NV center through this domain wall, whenever the NV center is near the domain region, the magnetic field has very high frequencies in terahertz, which does not couple to the NV centers, because as we just mentioned, NV center spins are splitted by gigahertz frequencies. And as a result, only gigahertz frequency fields can drive these NV centers. So if this NV center is near the domain region, a terahertz frequency comes out, and you cannot, this NV center sort of does not see this film, this domain. So on the other hand, whenever it brought near the domain wall, there is very soft low-lying modes, which couple strongly to the NV center, and as a result, can give information that where the domain walls are. And in fact, in a recent experiment, this was demonstrated experimentally, where what picture you see over here is a synthetic antiferromagnet. And whenever this NV center tip was near a domain wall, that domain wall lit up. On the other hand, whenever it was on domains, these domains were not that much visible to these NV centers. Right? So this is all about probing, let's say, the ground states of these systems. In a recent work, what has also been demonstrated that even the transport properties of these excitations above, the magnon's transpose properties, can be probed by these NV center spins, again, via the magnetic field signatures that these scattering processes of magnons show. Right? So that was what was demonstrated here. And finally, in this experiment over here, it was, as I just mentioned, you can use these magnons as probe beams, and through a target, it was scattered. And by imaging what is the scattering wave looks like via these NV centers, the phase information, the amplitude information of these scattered waves, one could reconstruct what is the scattering cross section, or what is the interaction. So you can start probing these sort of neutron scattering like experiments, but on a tabletop using magnets. So those are, in one words, the main type of applications that has been demonstrated. In the remaining part, I would like to dive a little bit more deeper into some of the new capabilities that these hybrid systems can possess. Demonstrating these new capabilities is what I want to show in the next maybe remaining 5-10 minutes. The first thing that I want to show is that the fact that I mentioned these magnons act like a chiral microwave source. That is to say that if I have a thin film, a magnon moving left and magnon moving right produces very different kind of magnetic field signatures. And that can be utilized to drive selectively a qubit or not drive that qubit. So that can give rise to various kind of mappings to, in the optics field, people talk about chiral quantum optics, where again, there are two optical qubits, and you want to just couple them in a chiral fashion. That has various applications. Same things can be done for these kind of objects if we can show the coupling between these two centers is chiral. And in this work, that's what we demonstrated. And that is one thing that I will dive a little bit more deeper into in the remaining time. And at the same time, this also shows that you can sense chiral phenomena. Right? So if you can sense chiral magnetic noise, you can use these centers to probe, for example, topological modes, one-way propagating modes. You can use these centers to, just by noticing the noise coming out of these one-way propagating modes, you can image these chiral modes. Another recent thing that we demonstrated here was utilizing this hybrid system was an electric control of this qubit. So as I just mentioned, that microwaves can be used to drive these spin centers, but now, since the fact that magnons can be controlled electrically because of the advancements that has been done in the classical spintronics, one can utilize all those phenomena to create these hybrid systems where an electric signal a voltage can start coupling to these NV centers. And this can give rise to the kind of scalable systems that I mentioned, can solve the challenge of utilizing these hybrid systems to create scalable quantum systems. And here we have also looked at another phenomena of utilizing the voltage control of magnetism to actually drive these. This is a theory work where we showed that you can, even at room temperature, drive these NV centers. Sorry, was there a question? Yeah, okay. And finally, the fact that now you can have electric field coupled to these NV centers, you can use this fact to start sensing electric fields using NV centers. Now, electric field can be sensed, as I mentioned, via Stark shift. But what we show in this work, by utilizing magnons as resonant enhancers, they can transduce this electric field into a magnetic field signature with sensitivities much larger than what can be done with electric fields. Right, so in the remaining maybe 10 minutes is what I want to show is one by one show a bit more details of these demonstrations that we just did. Okay. So first fact that I want to highlight is why the magnetic field out of these magnons, for example, thin films, create a chiral magnetic field. So something that we learned again in for spin wave excitations, it is the spin wave excitations can be written in the following form, that there is some net equilibrium magnetization above which there are deviations which are of wave-like, right? So they have some wavelength that is associated with them. So that's the typical type of an excitations of this magnetic film. Now, whenever we have this, and if I want to calculate the magnetic field such excitations will create, we can use the Maxwell's laws in the so-called magnetostatic approximation, where the magnetic field can be obtained, can be roughly in this magnetostatic approximation is proportional to just the H field that you, external field that you apply, and the magnetization at a particular location. And if I take divergence of this, we know divergence of B is 0 from Maxwell's law. So that means the divergence of H, if you want to calculate at any location, is created by divergence of M. And this is somewhat, you can think of divergence of M. Whenever you have divergence on M, that is magnetization, they act like magnetic charges, and that will create magnetic field, just like in electrostatics. Right? So this is basically, it's a long way to say that if you take a bar magnet, at the very end of it, there is a divergence of magnetization because the magnetization just end at the end of the magnet. And that creates North Pole and South Pole can be thought of as positive and negative charges. And if I create a wave-like excitations in the magnet, you will create this little dipoles of plus minus, and that will govern the value of the magnetic field. Now, it turns out that if a magnon is moving on the left-hand side, you create two kind of divergences. One at the surface, because there's a magnetization that there's no magnetization on top, but there's some magnetization inside. And at the same time, because of these type of wave-like excitations, there's finite divergence in the bulk also. So the net field is produced by these bulk charges and these surface charges. Now, it turns out that if a magnon is moving to the left and towards the right, the arrangement of these charges is such that in one case they add onto each other, and in another case they subtract onto each other, which you can see by plugging in this simple ansatz and calculating divergence of these magnetization. So as a result of that, what happens is in one direction, you create magnetic field which is rotating with a large magnitude. On the other hand, if the magnet wave was propagating on the right, it creates a magnetic field which is propagating in the other way with a smaller magnitude. And this is something that gives rise to a field, a magnon which is moving to the left gives rise to a field of a different strength and different chirality. And here a magnon moving to the right side is producing the opposite chirality and a smaller strength. So now, as a result of this, what happens is that if we place these NV centers on top of it, it senses very different kind of fields. And it turns out, interestingly, that NV centers themselves are chiral sensors. That is to say that if we come back to the Hamiltonian we discussed for this NV centers, in the first place, it was composed of some external magnetic field part, spin interacting with external magnetic field, and then there was an internal built-in field because of this center was lying in some lattice. So you can view this internal field also like some B dot S term. And if you view it like that, the internal field itself depends on the value of the projection of spin. Okay, so you take the derivative of this with respect to spin, you get a field which is proportional to the projection of spin. What that means is if I'm talking about these two levels between 0 and -1, where -1 talks about one projection And if you're talking about 0 and +1, where +1 talks about other projection, the value of the internal field that the center has flips because it depends on the sign of SZ. And because it flips, there is an inherent internal field which is of opposite sign in this NV center. Because of that, if this NV center is a chiral sensor, that is to say, if I come in and apply some rotating field, this rotating field will couple to one transition, but the other rotating field will couple to the other transition, which has other direction of the built-in field. So then the fact, if I combine these two facts, that is magnons are producing chiral fields of different magnitude and NV centers are chiral sensors of opposite senses, then one can actually see that if I put the two systems together on top of each other, one-way propagating magnons will couple more strongly to one of these qubits, one of these two-level systems lying inside these NV centers, but the other way propagating magnon will couple to other two-level system over here. And can we see this fact experimentally? Is that's what we focused on in this experiment, and we demonstrated that this fact indeed exists. And the way we do this is we utilize again these NV centers as very nice sensors of magnetic field signatures, because we can apply various kind of quantum sensing protocols in the NV centers to sense the value of the magnetic field. The particular sensing protocol we utilize is the so-called relaxometry protocol, which is based on the following fact that if I have a two-level system and I create some non-equilibrium population of this two-level system, it will relax back to a thermal equilibrium where the rate of relaxation to this thermal equilibrium is governed by the matrix element, by Fermi golden rules of the fluctuating fields that are coupling these two systems. So in one case over here, one type of magnons are coupling these two systems, and other type of magnons coupling the other 0 + 1 transition. So if you just monitor the relaxation rate of some non-equilibrium population of these NV centers sitting proximal to these magnets, we should see that the two rates are very different from each other because the strength of the field these two magnons produce is also different. And this is exactly what we demonstrate in this experiment over here, where we found that the relaxation rate of plus and minus were completely different from between these two systems. And just to give you a little bit more details of how exactly this is done experimentally, is we utilize this gadget that we introduced in the initial part of optically, you can initialize the system in the state 0 first by keep on shining green light, and then let it relax in the presence of these magnons and see how fast that relaxation happens. This was exactly what was utilized in our earlier experiment here, where we initialize the system either in the state 0 and ±1, and that's a non-equilibrium population, and let it relax to thermal equilibrium. The rate at which it relaxes carries the information of what is the coupling, what is the fluctuating magnetic field this sensor is sensing because of the magnons. And that's how you can sense what is the value of these fluctuating magnetic fields that are coming out of these things. Okay, and that's exactly what we did here. And here's some experimental results where I would like you to focus on this very left edge, where we are looking at the rate of plus minus relaxation, where plus minus is one of the qubits is the minus qubit, and another is the plus qubit. And we're just monitoring how fast that is relaxing. And when we are not applying any external magnetic field, then these two levels are almost at equal energy. And as a result, there should be no way that these two levels should be different in the relaxation rate. But what we observe, there's a very large difference. And in fact, if we now model these magnon spectrum and plug into the Fermi golden rule and calculate these relaxation rates, we were able to, without any fitting parameters, we're able to reproduce these levels if we include this chiral coupling in nature of these magnons. Okay? And that's something that shows that the coupling between these two systems is chiral. And as a result, now one can think about chiral quantum rather than optics on a microwave level utilizing these systems, which is a very interesting future direction. So maybe in interest of time, I'll skip the next part because I think I have hit the 50 minutes mark, and we'll be happy to take any questions. But if you would like, I can also go ahead and talk about the second part over here. All right, since I'm not hearing anything, maybe
question.
Yeah, sorry. Yeah, go ahead. Maybe I can come back to the screen, but let me just flash the last slide saying the main message that I want you to take away from this is the fact that a lot of progress again has been done in the classical side of things and on the quantum side of things. And hopefully what I've shown to you is, right now I just showed you an example of utilizing one of these excitations with this, but you can clearly imagine there's a lot of things that we can start combining with these quantum objects and start probing various kind of excitations and creating functionalities which can solve challenges within both classical spintronics and quantum spintronics, some of which I've labeled over here. But I'll be happy to stop here and see if there are any questions and talk in more details of if there are any interest of any particular one of them. So thank you again for listening to me. Okay, so I do see one question from Bhaskaran.
Hi, Pramey.
Yeah.
Sorry,
Hi,
can I
Bhaskaran,
ask the question now? I'm a little bit, I thought I interrupted, sorry. So,
yeah, no problem.
Is it okay to ask a
Actually,
question?
Pramey, actually, I request everyone to just hold on a second. We will take a group photo first. So, Pramey,
Sure.
could you kindly stop sharing for 30 seconds? And I request everyone to switch on the camera. And let's take a photo, then we will take the question answer. Okay.
Sure.
Thanks. So, Pushpendra, are you taking a pic?
Yes, sir, I'm taking the photos.
Okay.
Yes, sir, I've taken.
Okay. Thanks. So, Pramey, you can again share your screen, please. And we start the question with Bhaskaran. Bhaskaran, kindly unmute and ask your question. Thank you.
Thank you. First of all, Pramey, apologies if I could somehow interrupted your completion of the talk. Sorry.
No. Go ahead.
Yeah. So my question is very basic. Pardon my ignorance. So much of your work, what you discuss depends on the spin-Magnon interaction, right? How is that interaction? Is it similar to electron-phonon spin-phonon interaction? In that case, it will be Peltier and Joule effects somehow, right? Because somehow the spin can take energy from the spectrum and from the spectrum and can have dissipation as well as cooling, right? Just curious. Yeah.
Correct.
These are the two parts.
So at the microscopic level, the interaction is simply by the magnetic field. So, for example, in this case, whenever there's a magnon that is excited in the system, it generates a magnetic field that is shown in this green arrows over here. And this magnetic field just couples with the spin via Zeeman interaction. So it is just simply B dot S type of coupling between the two systems.
Like the Overhauser effect. Yeah.
Right. And now, again, if it's resonant, if the two systems are resonant, then you can, this interaction can transfer, for example, energy between the two systems, and you can cause Rabi oscillations inside spin. And so you can think about various kind of applications now, because you can, this system is driven by laser. So the things that you were mentioning, like you can utilize this for example, cooling magnons, because now you can preferentially populate these electronic spin in the state 0 by keep on shining light, and then it will keep on absorbing magnons from the system. And if you can again use light to quickly put it down to 0, so this will try to take magnons away from this nearby magnetic film, and that can give rise to cooling these magnons. So all the protocols that are there in the quantum optics type of community, one can start thinking about this in this direction as well.
Very nice. So last small bit is that, so one of the big problems in spin-based qubits, as you said, is a distant communication. And you feel that magnons can probably do the state transfer better than photons. I mean, right now people are doing it with microwave photons, etc. Right? So, or the
right. So microwave photons, again, with the NV center type of spin defects, it's challenging with microwave photons. What has been done is, as you're aware, it's with the sort of spin orbit qubits type of thing, where you still have some dipole moment, electric dipole moment, and then that electric dipole moment couples pretty strongly with this single spins. But just the magnetic coupling with this is very tiny. And for these NV center type of systems, it's very challenging to do single spin with some microwave photon coupling. Okay. On the other hand, magnons naturally enhance that interaction, and as a result, are better mode matched. So you can have nanometers type of magnons, and they can couple much more strongly.
Thank you very much, Pranay. Thank you for the very nice talk. It was very useful for.
Yeah, thank you, Master. Thank you, Pramey. There is a question in the chat box. You may kindly answer, read it and answer.
Okay, let's see. Thanks for the nice talk. It's really interesting. Is the NV center probing the static magnetic stray fields? Right. So it can do both. As I mentioned, it can go from DC to microwave, and that is actually a nice question. I should have mentioned that really depends on what protocol you are using on the NV center. So depending on what protocol, the protocol that I discussed towards the very end, this so-called relaxometry protocol. Let me go to that one. So in this relaxometry protocol, what happens is it's really the fluctuating magnetic fields that cause the transitions between the two. And that fluctuating magnetic field has to be resonant with this transition. Only then it will couple to it. So now this gap over here is typically gigahertz. And as a result of that, it couples to gigahertz fluctuating magnetic field, this particular protocol. So this particular protocol measures gigahertz frequency magnetic fields. Okay, so that is the up to that much frequency you can use. You can sense. You can also sense DC fields, and to sense DC field, a separate different protocol is used. The DC fields are typically sensing so-called ODMR protocol, which is sensing. So there's another -1 level, which I'm not shown over here. It's really DC field causes splitting between plus and -1. And now you can actually sense the difference between these two levels optically by looking at shining microwave. If you keep on shining microwave and tune the frequency of this microwave, it will be absorbed whenever it is resonant with this transition, and it will be absorbed whenever it is resonant with other transition. So by looking at those two absorptions, you can extract out what is the gap between these two levels. And this gap is proportional to a DC field applied along the NV center quantization axis. And that's how people use it to sense DC field. So now there are various other protocols where you can go right from this DC field up to gigahertz frequency. So all these frequency range can be sensed.
Yeah, all right. Thank you. There is a question by Arvind. Arvind, please unmute and ask.
It's very interesting talk, and I really learned a lot of things. So I have few queries regarding the size of this NV center. What are the typical sizes for them, for each?
Yeah, so each center is really atomistic. So you can think of it really one carbon atom on one vacancy, right? So the size of that is on the order of a few angstroms, right? So that's the atomic size is really the size of this. So, but I should also mention, yeah, sorry, go ahead.
Yeah, no, then the follow-up question will be, let's say you are using a Magnon and the wavelength, the minimum we go, it's actually in few nanometers. So that too, it's the exchange waves that is very high frequency. So how do you really couple Magnon with this angstrom scale?
So that's a good question. So the coupling here actually does not depend on the size of the NV center, but how close is that NV center to the film. Okay. So you can think of a Magnon. So again, let me try to draw it here. So if I have a Magnon on film, I'm drawing a side view. You can think of it, it just creates some bunch of plus minus charges. Because it has divergences in them, divergence of magnetization, and that creates like charges. And that is, roughly speaking, that is the field that comes out of these Magnons.
But that separation of the charges, right? It will be too far because the wavelength is too large for the Magnon.
Correct. So that's the right observation. So this separation governs what is the strength of field. But now how close I am, that also matters, right? So for example, if I'm too far off from this side, then I will average out all these plus minus charges and see nothing. These Magnons will not produce any field there. If I'm too close to this film, again, I will see nothing. It is as if you have a capacitor, which everything is just uniformly charged, and that capacitor will not produce any field outside of that capacitor. But if my distance is of the order of this charge separation, then I will couple very strongly with these fields. So it's really the wavelength needs to be comparable to the distance of it and not the size itself of the atomic sensor. That is the matrix element of coupling between two.
Really amazing that experimentally it has been achieved. I'm really looking forward to read more about that. So my next question, maybe the last one, if the time permits. So this, you have shown one more like a schematic where the magnons are like having, it's like a NV center shown as a defect and magnons are kind of getting dispersed. Or so again, the same question, like how magnons are getting like dispersed. It cannot be called a defect because the size is too small for a magnon. So how does that picture
Right.
get improved?
Okay, so maybe I think you're talking about, let me go to that picture.
And also maybe I'll add one more thing that have you tried anything like using STNO in this regard to use them as a local generator of microwaves?
Yeah. So let me answer both of them. Again, very good questions. So for the first one, I think you're referring to this picture over here on the bottom left, I believe, right? Where it's shown a target and it's scattered off
Yes.
it. So again, the key thing to keep in mind is the target from which it is scattering, that is still on the magnetic film. So you will create, for example, in this work, what was done was, this was a typical, for example, permalloy disc, a magnetic film disc put on top of big films. And then this disc size is sufficient, is comparable again to the wavelengths of the magnons. So it does scatter off pretty well from these things. Now, NV center, as I mentioned, the coupling to these magnons really depends on how far is this NV center from the film. And if you can separate it on the order of, again, nanometers, tens to hundreds of nanometers, that again matches the wavelengths that you're trying to probe. And you can get interaction information about that. So that's for the first question. For the second question, I did not had enough time, but people are really thinking about what you are mentioning also. So here's one example that I will show. Okay, so here is maybe the example. Here we are using, this is a theory work right now, not an experimental work yet, is where you use nanomagnet and you drive oscillations in the nanomagnet. So you were thinking about spin torque nano oscillator by using current to drive it. People are thinking about that too. Here I'm showing more voltage driving, utilizing so-called voltage control magnetic anisotropy effect to drive oscillations inside the magnet. But the principle is same. If you can drive locally the oscillations inside the magnet, these will produce local magnetic field at the NV center and will cause Rabi oscillations. What we show in this work is indeed, you can, even at room temperature, create very large quality factor drives for this NV center. One central challenge this field faces is there's also incoherent coupling. So you do want to couple with the voltage, but just this is placed at some temperature, right? So if this system is placed at temperature, you thermally also excite this magnet. That produces incoherent fields, which are detrimental for such applications, which you want to avoid. And the challenge is, again, how do you balance out the two? Can you separate out these detrimental effects? And what we show in this work that it is indeed possible to do that. And I'll be happy to talk in more details how we do that here.
Thanks very much. Thanks.
Okay, thanks, Arvinda. I think, Pramey, it's kind of about time. So we can wrap up. I request you to stop sharing. There are probably some more questions, but I think they can write you directly and we can discuss at a later stage. So,
Sure.
Pushpendra, could you kindly share the screen? So let me present a small token of appreciation from our team. So I will read it for you, Pramey. Thank you so much for giving this talk. It was really awesome, very informative. So W2S seminar, webinar series on Spintronics, National Institute of Science, Education and Research, NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Pramey Upadhyaya from Purdue University, US. In recognition and appreciation for being a valuable speaker to give a lecture on hybrid quantum spintronics. So on behalf of everyone, I clap. Thank you so much for this very nice talk. I hope sooner or later you can come in person to our campus. We'll be very happy to welcome you and host you. And let's catch up. And I hope also you can join future WTS seminars. And I look forward to your kind participation and also kind participation for the other participants who are here. Thank you so much, all of you, for joining this seminar. So I think it's time to stop, and I wish you a good night or a good day ahead, and see you next week. Yeah.
Same
Bye.
here. Thank you. Thank you. Bye-bye.
Bye.